Hi, everyone. Thank you so much for being here. My name is Lucy, and I'm really excited to take the next 25 minutes or so to walk you through some of the machine learning work we've been doing at Flatiron Health. Flatiron is a cancer data technology and services company based here in New York. We're still pretty young. We were founded in 2012. And the main goal of this talk is to share some of the context behind ML problems we're solving and give strategies we've taken to mitigate bias in the use of ML. For cancer research specifically. So before I dive into machine learning or Flatiron, I wanted to quickly introduce myself to give context for how I've interacted with these problems. I'm a software engineer at Flatiron. I've been there for about 2 years now. I've been working on the machine learning team. Before that, I was at Google here in New York, really close by. And before that, I was at school in Columbia. That's my Twitter handle. Also, if you have questions later, feel free to DM me. Okay, great. So here's the agenda for today. Given the healthcare focus of our meetup, I want to make sure I take the time to explain some of the healthcare context of the problems we've been solving at Flatiron. Then I'm going to get into some of the specifics about why we needed ML to solve these problems. I'll do a deep dive into a specific example applying ML for a problem called a cohort selection. And then at the end, I'm going to talk more about what bias is and the strategies that we've taken to address them. So to start, I want to give a brief overview of how cancer research is commonly done and how that motivates a different approach we've taken at Flatiron. So the primary way we learn about how cancer treatments work is through clinical trials. And with clinical trials, there's a common way that information flows. So usually researchers start with a hypothesis that they have about a treatment. And among all of the cancer, among the entire cancer patient population, they want to find the select few patients that can help them answer that question in a trial. Then they perform the trial and they publish on that in clinical research, and this is primarily what clinicians and patients will see to make treatment decisions. So in many ways, this is actually a really great way for research to be done. Trials are performed under highly controlled circumstances, and they provide reliable findings for clinicians and patients. But of course, this comes with limitations. So to start, they're slow. It's slow to find those patients that can help you answer the questions, and it's slow to follow them over time to measure the outcomes you're interested in. In addition, it's expensive, and the combination of these two things means it's actually hard to ask a lot of the questions that we want to ask. We're restrained by these two limiting factors. And in addition, a really big limitation is less than 5% of cancer patients in the US actually participate in a clinical trial. And what's particularly bad about this small number is the 5% that is in a trial is not representative of the broader patient population. So they're typically younger, healthier, and less diverse. To give like a very specific example, in the 5%, I'm like forgetting my numbers. I think it's 25% in the 5% are above the age of 65, but in the broader patient population, actually 60% of real-world patients are over 65. And something else that's sad is it's not that the 95% who are not represented aren't interested in participating in a trial, they actually don't have access in many cases. So given these limitations, what can we do to improve this picture? So the solution Flatiron pursues involves another source of data that's not yet reflected here at all. So I've mentioned that there's a great limitation to clinical trials, which is the patients there are not necessarily representative of a broader patient population, and that also means the outcomes are hard to translate to the broader patient population. And so there's this opportunity to look for exactly that data, the data about what happens in the broader patient population, and that data, known as real-world data, does exist, and a major source of it is the EMR, or the electronic medical record. And this is where doctors are recording day-to-day what is happening with their patients. So you may have heard about how EMR data is really messy or decentralized or hard to learn from, but there is an opportunity. So the really exciting thing about high-quality real-world data is that it can be used to generate real-world evidence, which is something which is clinical evidence about the usage and potential benefits of a therapy, so specifically in our case, cancer therapies. And as the word evidence suggests, it means that real-world evidence is useful for research, unlike the messy data that you might have heard of before. So at Flatiron, we have this mission to learn from the experience of every cancer patient, not just the 5%, that small group. We want to learn from everyone. And so we've gone after the data that's locked away in electronic medical records. So we've made progress towards our goal by looking for this real-world data, and more specifically, generating real-world evidence from it. So when delivered back to researchers, they can generate insights over de-identified data, and when delivered back to clinicians and patients, they can learn about how treatments that they've seen in trials will actually work in the patients that they see day to day. So to briefly describe how we've actually done this, the first thing we had to do is go out and build that source of real-world data. And so the first step we took was building a pipeline of that real-world data, and we did exactly that. We found this broad patient population across the US to learn from, and we have a network of about 2.1 million active cancer patients in the US, seen by 2,500 different clinicians across 280 cancer clinics. This is much broader than the patient population you'd ever see in a clinical trial. To be more precise about what it means to be a part of Flatiron's network, cancer care providers become a part of our network when they start becoming users of our provider products. So actually a large group at Flatiron spends their time building products specifically for cancer care providers. For smaller practices, which are commonly known as community cancer practices, they use our oncology-specific electronic medical record system, which is called EMR. For the big academics, we have a specific product for them, which is a layer on top of their EMRs, frequently like Epic or Cerner, which you may have heard of before. So with that large network of providers and real-world data, Flatiron has developed and scaled various processes to centralize, standardize, and otherwise transform real-world data into real-world evidence that's usable for research. Very exciting. Okay, great. So that's kind of the context. Flatiron has developed capabilities to create real-world evidence, but I haven't yet introduced where ML comes in, so I'm going to speak to that next. So to start, I wanted to highlight a principle about machine learning that we have at Flatiron, which is this. We don't want to be that proverbial hammer looking for a nail. We turn to ML when it helps us to solve a problem that we have, not for ML to be a product in itself. So a big problem that our non-machine learning tools were starting to have trouble with was with this part, which was converting that real-world data to real-world evidence. And there's a specific subset of the data processing problem that I wanted to focus on. So the EMR typically contains two types of data. There's structured data, which you can imagine is the kind of data that comes from checkboxes or drop-downs or multiple choice menus. And there's also unstructured data, which is more the free-form text that might be generated when a doctor is typing up a note at the end of a visit, or it's the facts that you get from the radiology department. Any of these types of messy free-form information is known as unstructured data. So if you were to guess which one is harder, you would probably guess it's the unstructured data processing problem, and that's true. And to make the whole kind of problem of generating real-world evidence even harder, most of the data we're interested in, unfortunately, only exists in unstructured data. So to give context for why this is a hard problem, I want to introduce just one example. So imagine that you're trying to do research on lung cancer patients, and so you've found a population of lung cancer patients, and you're really interested in figuring out which of them is a smoker. So that sounds like something that should be a checkbox, or at worst, some kind of confusing multiple choice menu, but frequently that's not the case. Even if you present that checkbox in the EMR, it's not always going to be used. So here, this is where you might actually look for smoking status instead. So you end up with a doctor's note that records everything that a doctor found out in a day. And so you're now going back for research purposes and trying to figure out, was this patient a smoker or not? And you have to do this for many, many, many patients. If you look really carefully, you'll eventually find it. So in this case, it's just one small piece of information, denies smoking. So that takes a lot of effort. So what have we done to make this, to approach this problem? So one solution we came up with is known as Technology-Enabled Obstruction, which relies on abstractors who are clinically trained experts, people who really understand cancer data, who've worked with cancer before, and we have them manually review and curate unstructured text into the information important for real-world evidence, for research. So using Flatiron internal tools to do this was a process that actually scaled very well. To give you an idea of like the magnitude, we started abstracting over 100,000 patients a month, and we have over 1,000 abstractors across the country doing this. But recently, even that wasn't enough, despite like how large of a process that sounds like, it's not enough. The demand for unstructured data processing is growing, and we knew we needed to consider other tools to help us scale this capacity. So this is a slight oversimplification, but I want to categorize the kinds of problems unstructured data processing problems we're solving into two types. The first is known as cohort selection, which is organizing patients into useful groups for research. And here's an example list. You'll see that most of them are organized by disease, which kind of makes sense. And then the second unstructured data processing problem we encounter is extracting data points important for those specific groups of patients, those cohorts. So for example, for lung cancer, like I mentioned, you would be very interested in smoking status. Okay, so now that I've broadly introduced why we need to consider machine learning to enable us to generate RWE at scale, which is to answer those groups of questions at scale, I'm going to go into an example of a specific cohort selection problem to show how machine learning fit into the solution. So the example I'd like to dive more deeply into is specifically cohort selection for metastatic breast cancer. So our goal here is, of our broad patient population, we want to find all patients who have metastatic breast cancer. We want to organize that cohort so we can do research on that population. To define the terms a little bit more clearly, metastatic refers to when cancer is spread across the body. So it's typically late-stage disease. There's also early breast cancer, which is not the same. And so the big challenge is we have to search unstructured data for each candidate patient. So we first have to find which patients might have breast cancer, then you have to figure out whether or not they have metastatic breast cancer. And so the kind of like the information flow to do this is outlined here. So this is what cohort selection looks like without machine learning. So we start with a structured data processing problem because there's actually a good structured data filter to figure out which patients might be in this cohort. We can actually look at billing codes to figure out who we think has breast cancer. There's no indication for who might be metastatic, but we can get a good sense of who might have breast cancer. So every patient selected by the structured data processing filter, we then send to abstraction. We send to these clinical experts to manually look through all of the documents and figure out which of these patients have metastatic breast cancer. And once they confirm, those people will be included in a cohort and the others are excluded. And so there's one number here I want to highlight that is particularly motivating for making this a good problem for machine learning to solve. So we spend a lot of our limited abstraction resources actually looking at patients, looking at documents for patients that don't even make it into our cohort. 89% of patients that we have expensive abstractors look at don't even make it into our cohort. So when we're thinking about how we can manage our increase in demand for unstructured data processing, this was like a good opportunity for us to consider machine learning for. And so what we did was we added machine learning as like a filter in between the two steps of filtering. So in between the structured data processing and the unstructured data processing, we now have this layer of machine learning. We now have these patients that the structured data suggests might have breast cancer. We have a machine learning model look at it and ask, does this patient likely have metastatic breast cancer? If yes, then we'll have humans confirm. If not, we can exclude them. And so this actually had really good results. We were able to reduce abstraction burden by about 74%. The ML model wasn't perfect, but it found almost all of the patients. So this might be a great place to stop and congratulate ourselves for improving the efficiency of cohort selection, but it's not quite that easy. We're not quite done yet. And that's because we have this problem of bias. So bias is a slightly overloaded term in machine learning, so I want to be very clear about the kind of bias we're referring to here. So machine learning models can systematically make similar errors, and what that leads to is the predictions are biased by those errors. So I want to explain with a fairly simple example. So imagine you have a machine learning model to predict college admissions. A positive prediction means that you're predicting someone will get into a college, and a negative prediction means you're predicting that they won't. So you could get most of your predictions correct. This model could get most of the predictions for students. I substitute a lot. So for most predictions for students, you could get it right. But what if you missed just a few, and those few are always from the same state? Or what if those few are always from the same major? That model is biased despite how high quality it might seem. And so this is actually one of the big issues with bias. It's a biased model might appear to be high performing by other metrics. So a commonly used term for measuring the performance of a model is sensitivity. You might have also heard of it called recall. And that measures the proportion of actual positives that are identified correctly. So in the college prediction case, if you can correctly predict most of the students who will actually get into the college, you might have really high sensitivity, but you still have to worry about the few students you miss. What if they're all in the same major? What if they're all from the same state? And so applying this to Flatiron's domain, the risk is particularly worth addressing. So if a machine learning model, in our case, excludes patients systematically, the resulting cohort could be clinically biased, and this is something we really have to worry about. So to give an example, let's say the sensitivity of our model is associated with quality of care. Our model could be extremely high performing by a common metric like sensitivity. We find almost every metastatic patient and include them in our cohort. But what if that's correlated with how the quality of care that patient is receiving? And so if we have this kind of bias in a model, cohort selection would exclude patients with lower quality of care, biasing the resulting cohort and the research that you could do with that real-world evidence. So if we deliver this kind of data, we have to worry about incorrect conclusions being drawn from it. And in the worst case, this could lead to something like incorrect recommendations on how to care for patients. So even though we have this promising way to accelerate cancer research, and we have shown that ML could help us generate more real-world evidence, we really have to think about this risk. So because of the magnitude of this responsibility to think about this risk, we've come up with some strategies to mitigate bias. And I know we're talking very much in the domain of healthcare, but these are also strategies you can apply to other high-risk situations where you want to use machine learning. So to start, you want to select, training, and test set patients randomly. So the training and test set patients are those that we use to train our model and assess its performance. And these are always labeled by hand. So it's a curated golden data set where we've made sure that we know whether or not these patients are truly metastatic or not. Why is it important for them to be randomly selected? The big reason is patients in our training and test sets should be representative of the total patient population. So we want to make sure that all clinically relevant subpopulations, so subpopulations of different age groups, gender, or stage of cancer, we want to make sure all of those subpopulations exist in similar proportions in our test set and training set compared to the real population, the broader population of all cancer patients. The subpopulation representation is crucial to help prevent and detect the case where a certain population is systematically missed by the machine learning model. So imagine if our training data didn't have any male patients with metastatic breast cancer. It could learn that male patients never get metastatic breast cancer, which is not true. And similarly, if our testing data didn't have male patients, we also wouldn't be able to detect that mistake if we were making it. So next, we have this strategy, which is to examine clinical characteristics of ML-chosen cohorts. And so this strategy is more about detection. So I've mentioned that things like sensitivity, also known as recall, is a good way to assess, is a way you can assess the performance of a model. But even with really high sensitivity, really high recall, let's say 98, 99%, you still have to worry about that 1%. And so in order to think about this, we've developed a strategy to examine the clinical characteristics of what happens if you use machine learning to select a cohort versus manual review, so manually. And so if we assume that our test set is representative of the total patient population, so assume that we've established, because we've selected them randomly, that we have a fairly representative population in our test set, the next thing we want to confirm is that the patients selected by our model in the test set are still also representative of the broader patient population. And so what we want to do to assess this is we need to subset our data we need to subset the test set in two different ways. So the test set consists of patients who are metastatic and patients who are not. And so the first subset that we want to essentially single out is the subset of metastatic breast cancer patients identified by manual review. So I mentioned this is like the golden data. So these are the patients within the test set that we know for sure have metastatic breast cancer. And we call this the reference standard. And the second subset that we want to take from this test set is the metastatic breast cancer patients identified by the machine learning model. And what we're interested in is the difference. And we want to compare these two subsets for any evidence of bias. So like assuming the machine learning model just made a couple mistakes, we want to figure out, are those mistakes random, or did we introduce bias because we forgot all of the male patients, or we couldn't detect some low quality of care, for example. And so the way that we compare these subsets for evidence of bias is we ask a very specific question, which is, do the distributions of clinically relevant variables look different in the ML selected cohort compared to the reference standard? And so tangibly, to answer this question, what we do is we calculate and graph many domain-specific clinical variables. So in these plots, for gender, race, and agent metastatic diagnosis, you'll see kind of 2 bars per subgroup. The gray bar is the subpopulation found by the machine learning model, and the green bar is the kind of golden data, what's found by human curation. And you'll see across these 3 variables that I've chosen as examples that it's actually the same. If we missed 1 or 2 patients, you don't see that evidence of bias. To give an example of something that would look bad is, like, for example, what if we missed like an entire bar in the agent metastatic diagnosis? If one of the gray ones was substantially lower, that would indicate bias. So these are just a couple examples. I wanted to point out that there's also dozens of others that we also compute to ultimately assess bias across many different axes. And so we've talked about how we can reduce the risk of training a bias model. I've also talked about how we can supplement performance measurements like sensitivity with a new way to assess for bias, for clinical bias, but I do want to conclude with a strategy that addresses a more time-based risk. So the thing about unbiased models is they can become biased. If patients that you're newly adding to your EMR look clinically different from patients that are already in your EMR, over time, your unbiased test set can become stale. It can become biased. And so in order to ensure that our model is not temporally biased in this way, we want to regularly add patients to the test set and the training set and retest our model. And so this allows us to capture 3 different kinds of changes that we might see in the real world. So there might be changes in treatment patterns, changes in documentation patterns, and changes in Flatiron's network. To give you a more concrete example, let's say in 2019, a new drug is approved for treating metastatic breast cancer. And all of a sudden, everyone who has metastatic breast cancer is being treated with this new therapy. Our old machine learning model that was trained in 2018 would never learn to associate mentions of that therapy with metastatic breast cancer. So as we add to our training and test set over time, that's the kind of difference that we want to capture. And the same applies for changes in documentation and changes in our network. And lastly, I did want to point out that in addition to measuring things like sensitivity to assess those things, we do want to make sure over time we're regenerating all of these analyses. So that's the last strategy I have to present today. But before I finish, I just want to really quickly give a summary. So we've learned that real-world evidence is an important tool for improving cancer care. And at Flatiron, we've looked to machine learning to really accelerate the creation of real-world evidence to allow us to enable a lot more research. But using ML in this setting comes with risk. And I've talked a lot about the bias cohort risk. But we have built up the confidence to use machine learning by implementing the various strategies that I've walked through to mitigate this bias. Okay, that's all from me. Thank you so much for being a great audience.